6.1, we're going to think about sampling distributions here. So in 6.1 it says here, let's say there was a midterm given, these are the scores. Today we're going to be taking a sample from a population, so remember these from previous terms, this is everybody, and we're taking a sample, a few people from everybody, and we're going to use the average of that sample to estimate the average of the whole population. Okay, so let's just start very basic. Let's say only 4 people took the midterm. So these are those 4 scores of the midterm. Okay, so this right here is our population. If there were only 4 people that took the test, okay, let's say there was only 4 people in the class. Okay, so let's say we take a sample of any 2 scores. Let's say I randomly choose, and I choose the 70 and the 90. Okay, this is called our sample mean. Okay, so X bar is the symbol we use for sample mean. Okay, so our sample mean is 70 plus 90 divided by 2, which equals an 80. Okay, so that's just one sample that we took, and we found the mean of that sample. Now, if I figure out all possible, okay, so if I think about these numbers here, all the possible combinations, could be the 60 and the 70, could be the 60 and the 80, could be the 60 and the 90, could be the 70 and the 80, could be the 70 and the 90, could be the 80 and the 90. Okay, so these are all the possible choices we have there, right? Okay, so if you think about how many there are, think back at another chapter. The first one I could pick one of 4, and the second one, once already picked, I could pick one of 3, so there's a total of 12 different one. Well, considering they're back and forth anyway, so we should actually use combinations there, but anyway. Okay, so that's why there's only 6. But here we have our different samples that could be collected. If we find the mean of these 2 added together divided by 2, we have an X bar that equals 65. Here we have an X bar is equal to 70. Here we have an X bar equal to 75. X bar equals 75. X bar equals 80. X bar equals 85. Okay, so these are samples that are taken from a population, and this is the mean of these samples. Okay. Now, if I make a dot plot of this data, okay, so 65 was the lowest. Okay, so we had a 65, we had a 70, a 75, a 75, an 80, and an 85. Okay, so this is called a sampling distribution. That's what this whole chapter is about, a sampling distribution. So thinking about what this means. Okay, it's a distribution of these, right? So what do each of these dots mean? Okay, so each dot is a sample mean. Each dot is an X bar. Okay, so a sampling mean is of all possible outcomes. Okay, so it's not just that I took, if I have this as my population, it's not just that I took 1 or 2 samples. I take all possible samples of size 2 in this case. Okay, and that's my distribution. Okay, the actual true mean, if I take 60 plus 70 plus 80 plus 90 and divide by 4, okay, that comes up to be 75. And you notice that's right in the middle of my distribution right there, right? So we call this unbiased. And we'll get to that term a little bit later, okay? Because the true mean of our population is equal to the mean of all of my X bars, okay? We'll talk more about that a little bit later though sometime. Okay, so yeah, a sampling distribution. It shows that the mean calculated from all of the possible samples of size 2. Okay, so from all possible samples. Okay, so, but really there are more people than, well, let me explain these 2 symbols here too. Okay, so we have something called a parameter, and we have something called a statistic. Okay, so in a parameter, whenever we talk about the parameter, we're talking about the population. And whenever we're talking about a statistic, we're talking about the sample. You can think SS and PP. Okay, so you can think about those 2 things there. Now, if I'm talking, these are the different symbols we're going to use. So if we're talking about finding the mean, we kind of talked about that here. A sample, we'd use X bar, and if we're talking about the population, we use mu. If we're talking about a proportion, we're going to use P for our population, and P hat for our sample. And we're also going to talk about standard deviation. Standard deviation of our sample, we use S, so like S of X or whatever. And for the population, we use this. Okay, so those are some things you should be familiar with, knowing the difference whether we're talking about a population or if we're talking about a sample. Basically, if you see a Greek letter, we're talking about a kind of a population, and if you see kind of these symbols here, we're talking about a statistic, a sample that was taken. Okay, so in reality, there were many students who took the midterm. So let's say we have this many people who took the midterm. We had 146 people that took a midterm. Now, let's say I want to collect a sample of 5. Okay, so you could say like, hey Google, or hey Siri, give me a random number between blank 1 and 146. So 1 and 146. Let's say I come up with random samples. I go, hey Google or hey Siri, you get random numbers, or use random.org, right? Let's say I got random samples 2, 10, 20, 100, and 126. Okay, just kind of making that up. So score number 2 was a 97. Score number 10 was a 75. Score number 20 was a 49. That person didn't do so well. Score number 100 was a 77. And 126 was a 58. Okay, so that's my sample that was collected. Okay, so this right here, this is my whole population, and these are the sample scores that I randomly chose. Okay, now I'm going to grab my calculator here. I'm going to find the mean. Taking a sample of 5, my mean, my x bar is equal to 70.6. Okay. So that is just one sample. Okay, so if you're thinking about a sampling distribution, okay, so I know that one score was like if it was between 70 and 71, 70.6 was one sample that I collected. Okay, we would do that over and over and over again. Okay, do over and over and over again, and I'll just tell you that I'm going to pause this and kind of get what a sampling distribution might look like. Okay, so if I did what I did a bunch of times, right, randomly chose 5 numbers out of here, right, out of all the scores, and chose their scores and average those together, right, so if I randomly choose 5 and find their mean, and I do that a lot of times, I get this. Okay, now this is not technically a true sampling distribution because I don't have all possible answers. So if you think about 146 different numbers, right, how many different combinations of 5 could there be? So if I think about, you don't have to really know this, but if there's 146 different, and we talked about combinations of choosing 5, there would be that many dots I would have to put on there. So that a true sampling distribution would have over 515 million different dots. Now that's not going to happen. I'm not going to find all those. It would take me a year to do that or more. Okay, so I'm not going to do that. So this is an approximate sampling distribution because I don't have all the possible things there. Okay, but if we think about this, what does each dot represent? Okay, each dot, so for example this dot here, okay, is a sample of 5 scores and the mean of that. Okay, so each dot is a random sample of 5 scores that I collected and finding their mean. So I did it again, found their mean, did it again, found their mean, did it again, find their mean, and I get a whole bunch of dots there, right? Okay, so a sampling distribution shows the mean calculated from all possible samples. Now, is this all possible samples? I said no. Okay, there would be 146 choose 5, which was different samples collected if I got all. Okay, so I don't have all possible samples there, right? Okay, so let's just say that we got we took a random sample and of 5 scores, and we got a mean that, oh, by the way, the true mean, okay, the population mean was 75.98. Okay, so that means if the whole population, if I took all 146 of these scores and added them all together and divided by 146, it came up to be this. Okay, notice my sampling distribution was, the center of it is right around where that is, right? Okay, that means it's unbiased. We'll talk more about that another day as well. But each of these is an X bar, right? That's an X bar, that's an X bar, that's an X bar. The true mean population was this amount. Okay, so let's say we take a random sample of 5 midterm scores and got a mean that was a 68. Here's 68, right? So we got a sample here. Is it convincing evidence that this other school did worse than students at our school? Okay, so if these are the students at our school, and we took a sample, did we have any samples that were that low? Okay, nope. So if I took a sample of this other school, so yes, there is convincing evidence. As we didn't have anyone, right? None of our samples collected gave us that low. None of our sample means were that low. Okay, so that's thinking about what a sampling distribution is. Okay, so now we're going to talk about how does changing the sample size affect our sampling distribution. Okay, this is another important topic here. So if I had a sample of 5, right? I had a sample that looked like this. Okay, I have it right here. Okay, I kind of just drew it here. Okay, it looks something like this. Now, let's say instead of choosing 5 scores from here, I'm going to choose 10 scores from here. Okay, so I do a random number generator and I pick some random numbers. And let's say I pick numbers 1, 15, 23, 40, 85, 1, 2, 3, 4, 5, 86, 90, 130, 140, and 146. I don't know, just random. Let's say those are randomly chosen. Okay, so my scores. Person number 1 had a score of 60. Okay, score number 15 had a score of 74. Number 23 had a score of 78. Number 40 had it well. Number 85 got an 81. Number 86 got a 97. Number 90 got a 59. Number 130 got a 61. Number 140 got a 69. And 146 got an 83. Okay, so randomly, let's say I just randomly chose those numbers with random number generator, and I found them. Okay, now to find their mean, okay, I have to take them and add them together, divide by 10, plus 97, plus 59, plus 61, 69, and 83. I add them together and divide by 10. I found an X bar, a sample mean that was 76.2. Okay, now we had said the true mean was right around 76, right? So that's pretty accurate, right? Okay, now let's say I did that a bunch of times. Okay, I did it, a lot of different times, and I had you do a bunch of times, and I had everyone in the class do it a bunch of times. How do you think it would be different than this? Okay, here's when I chose a sample of 5. Here's when I chose a sample of 10. So if I take more in my sample, what's going to happen to this distribution? Okay, I would tell you that the distribution, let's see, I use the same scale here, right? Okay, if I had, okay, so I'm thinking about this distribution. I'm still going to have the center around 76, just like this is, but it's going to be a lot less spread out. So my standard deviation is not going to be as large. My standard deviation is going to be smaller. Okay, so I'm going to have more numbers right around this area here, and they won't be as spread out. Okay, so increasing the sample size decreases spread, or the standard deviation. Okay, so if I have things more spread out, I have more in my sample, stuff is going to be less spread out. Okay, so some things to make sure you know. We said our parameter is the population, and we said our statistic was our sample. Another thing we had talked about was the sampling distribution. Okay, is a values of a statistic for all possible samples. Okay, so like in these cases right here, when I was choosing from this, remember we just chose a bunch of points, it wasn't all possible outcomes, right? Because remember that was like 500 some million, right? Okay, so those weren't true sampling distributions; they were kind of approximate. Okay, and the third thing we talked about was if we increase the sample size, then it has the effect of decreasing the variability. Okay, the more in our sample, the more accurate. Okay, so if we think about this information, let's do a problem together here. A fast food restaurant promotes certain foods by giving the name a game piece with each item. Advertisements proclaim that 25% of the game pieces are instant winners. Okay, you go to McDonald's, buy something, 25% of the time you're going to be a winner. To test this claim, they somebody goes there a bunch of times, they collect 20 game pieces, and they only get 3 winners. So 3 out of the 20, they only won 15% of the time. They said 25% of the time people win, but we only got 15%. Okay, so let's identify our population. Okay, our population would be all the game pieces. Okay, thinking about population, our parameter, right? Okay, which means our parameter, we're thinking about what we're trying to measure, right? What we're trying to find out. Okay, is the true proportion of game pieces that win. So they say it's 25%. Maybe it is, maybe it's not, but that's what we're trying to find the parameter. Okay. Our sample were the 20 pieces collected. Okay, we collected 20 pieces, and which means our statistic. Okay, we're talking about proportion, so it's not our parameter. We're trying to find p, right? We're trying to find p. Our p hat, our statistic, was the proportion of winners in our sample. Okay, and we already had a p hat that was 3 out of the 20, which gave us 15%. Okay, so suppose the advertisers are correct and at 25%. Okay, so we have a center here around 25%, right? So we did a sampling distribution. Okay, we did a whole bunch of different samples of size 20. So some 30% of the time, 25%, 20, etc. Okay, and here are 100 different things. So we did 100 times. So we collected 20 pieces once, 20 pieces twice, 20 pieces 30 times, and figured out what percent of the time they won. Okay, so would it be unusual to get a sample proportion of 15% or less? Okay, so 15% or less would be this area right here. Okay, and that's what, 1, 2, 3, that's 18 out of the 100 times, which is 18%. Therefore, that's not that unusual. We say that if it's less than 5% or 10%, then we would say that it is unusual. Yeah, okay, so based on part 2, based on this information, is there evidence that fewer than 25% of the pieces are instant winners? So they claim it was 25%, right? We got 15%. Is that enough evidence? No. Could have happened. By chance. Okay, this is the whole idea that we're getting at for a statistical significance test, which we're not really going to get to, but we're getting the ideas behind it right here. So in this problem here, we want to identify what is our population, and then from our population, what's the parameter we're trying to find, and what is our sample, and from that sample, what did we collect? Okay, what statistic? So Research Center polled asking 1,102 12 to 17-year-olds in the United States if they have cell phone. 71% said yes. Okay, so our population are all the 12 to 17-year-old in the U.S. Okay, and our sample would be the 1,102 12 to 17-year-olds. Okay, now what do we want to find out about the whole population, and what did we find out from our sample? Okay, from our sample we found out that the proportion of those that had cell phones was 71%. So since it's a sample, talking about that, the statistic is p hat, and we want to know what p is, which is the true proportion of those with cell phones. Okay. Okay, so part B. Do the same thing here. Okay, so Tom is roasting a large turkey breast for a holiday meal, say Thanksgiving. He wants to be sure that the turkey is safe to eat, which requires a minimum internal temperature of 165 degrees. Make sure it's fully cooked, so salmonella is not there, okay? So Tom uses a thermometer to measure the temperature of the turkey breast at 4 randomly chosen points, and the minimum he gets is 170, okay? So the sample he got was the measure at 4 random points. Okay, that's the sample that he got, representing the population of all the turkey breast. Okay, so of the whole breast, he chose 4 different spots to take a sample. Okay, and it's supposed to represent the whole turkey breast. And the stat that he got was a minimum of 170. And what we want to find about the whole thing is, what is its minimal temperature? Okay, there's no symbol we use for that, like P and P hat, but just we can just say minimum there.